All right, so you should have picked up a graphing calculator when you walked into the room today. What I'd like you to do is I'd like you to start by double tapping the on button, because who knows what they were doing in the last class with them. Okay, when you do that, you get this screen up here. You want to go with a new document, and no, you do not want to save your last document. Okay? We're going to be talking about graphs here today, so you're going to want to open up a graph page. Okay? So that's where we want to start today, and what I would like you to do is I would like you to start by graphing x equals 3 cosine of theta, y equals 2 sine of theta over theta from 0 to 2 pi with a t-step of 0.13. Okay, so graph this first one for me right now. Alright, so first thing you got to do is you got to change this over into a parametric, because now I can see what it is. And then I'm going to go 3. If I type in, I got to type in times first. If I type it in, I for sure got to do the times, and then it's cosine, and then I got to open up a set of parentheses, and then it can be t. If I do it the other way, if I do it with the trig function, sine of t, then I think last class I think we still had to do the times in there. Okay? And so then, oops, I went too high. So then when I do that, I get that. What figure is that? What do you got? It's an ellipse, yes. It's not an oval. Its technical term is called an ellipse. Love it. We've dealt with ellipses before, correct? Yes? Okay. So what I want to know is, actually let me do this first. Let's go here and there, and there it is. That looks so prettier. And then that one, and then we'll bring it up into her. And then, so talk to me now about said ellipse. What can you tell me about this particular ellipse?
It's centered at the origin.
Very good. It does have a center. Its center is at the origin. What else can you tell me about the ellipse? Because I need some more information, because that really doesn't tell me much. It's 2. So is that major or minor? Because in ellipses we talk major and minor axes. That's minor. So the minor axis has a length of 4, right? Because it's 4 all the way across. Okay. What else can you tell me? Major axis is 9. Or excuse me, 6, yes. Anything else? Now, really going to put the old, ear space filler to the test now. Okay? Back in first semester, when we were doing conic sections, what was the equation of an ellipse centered at the origin with a major axis that had a distance of 6 and a minor axis that had a distance of 4? What's the equation from first semester of the conic section centered at the of the ellipse, centered at the origin, minor axis length of 4, major axis length of 6?
Yeah, x minus h squared.
X minus what?
H squared.
So what's h then?
0.
So I could just say x squared?
Yeah.
Okay, love it so far.
Over.
Over what? But what's a? No.
3.
No. What? 3.
How in the world? Oh,
That's it? Just x squared over 9? Plus. Okay. Ellipses were pluses. Yep. Y squared because it's really y minus k, right? Okay. So it's y minus 0, so we'll just call that y squared. Over, no. Over 4. Yep. Over 4. And now here's the important part. For an ellipse, it equals 1. 2 up. From the origin, from the center to the top, or to the vertically, that's the x, or the b I should say. And from the center to the vertice, okay, because that's the endpoints of the major axes, was 3. Love it. Now, what I want you to do is now, I want you to eliminate the parameter, and you'll know you're done when you get x squared divided by 9 plus y squared divided by 4 equals 1. Be honest with me. Who's got an inverse trig function in their equation right now and they're stuck? Okay? Somebody wasn't paying attention on Friday. So, when our parametric function is trig-based, which in this case it's trig-based, and I want to eliminate the parameter, what do I have to solve for? So I want to use the hammer, right? Okay, so if I'm going to use the hammer, then I should take x equals 3 cosine of theta, and I should make that become cosine of theta is equal to x over 3, correct? Okay, and then I should take y equals 2 sine of theta, and I should make that become sine of theta equals y divided by 2. Love it so far. And then you said what, Ben? Use the hammer? Yeah. Well, knock, knock, knock. The cosine squared of theta is equal, oops, it's not equal to, tap the brakes, Linsmeyer, plus sine squared of theta is equal to 1. Because that's the hammer. Learned it long time ago. Number 9 on your formula sheet on your unit circle. Okay? I haven't done anything other than write the hammer down yet.
I thought you turned those.
No, haven't done anything yet. Yeah, that's why I was a little confused. Hoodwacked. Befuddled. Okay? So now I got to take this cosine and I got to square it. I got to take this sine. I got to square it. And that's going to equal 1. Well, that's going to be x over 3. And the sine is going to be y over 2. When I squiggity square those two, I get x squared over 9. Wait a second. Things are starting to come together. Plus y squared over 4 equals 1. What? And that's my blue equation that I should have gotten from first semester. Okay. Oh, yeah. Hartman? Yeah. We're fighting. Okay? Now, this next one, I just want you to graph. I don't want you to eliminate the parameter on. So, let's graph that one. Graph me the spiral of Archimedes. Yeah. graph that. You're going to have to notice a couple of tweaks here. Okay? Tweak number 1, you're going to have to adjust your t values. Tweak number 2, you want to probably adjust your window too.
No, I put this thing.
Alright, so I'm going to start a new page because I like new pages. Alright, so we got a graph, yeah. Then we got to go menu, and we got to go entry edit, and then let's go metric, and I don't want 2, I want to go 3. Okay, so then now I got to bring this down so I can see what I'm putting in here. So I got to go t times the cosine of t, and I got to go t times the sine of t. I got to change this to 4 pi. I got to change, oops, I got to hit enter, and then I got to change my window, or my window setting in 20s, 20s, and 15s. So negative 20, 20,
Oh, there we go.
2, 15, 15, let's go by 2. Oh, snap.
Yes. Well, that is not right.
Oh, don't like it. Let's get rid of it. Back to here. Sleepy. There we go. Now I like it. Yes'm? Yes'm. All right. Love it. Woo, woo. Try that one. This one is kind of funky. This one's really funky. So that's what I got after I typed it in. Looks like a pumpkin on its side rolling down the street. Some people said it looked like a basketball.
Looks like a peeled orange.
Peeled orange. Yep. What's wrong?
Nothing. I'm just looking at it. I'm like, because I was looking at it, I was like, pumpkin. How do you see pumpkin?
Turn your head. Turn your head like this.
Did you see that? I had my head turned like that. It was like, oh, there's the pumpkin.
Yeah, buddy. Awesome.
That's because you go back.
Love it. Love it. Love it. Love it.
No, because I was looking at the board.
All right. So now we're going to go away from the calculators for a little bit. We will come back to them momentarily. Okay. But we're going to slide on off away from them for just a squash. Okay. So if I am dealing with the unit circle, and we've been dealing with the unit circle for many, many moons now, okay? So any point that is on the unit circle has an ordered pair of what? What's any point on the unit circle has an ordered pair? Cosine theta, sine theta, or cosine of t, sine of t, right? Okay. So it has an ordered pair of cosine of t, sine of t. Okay. So if I wanted to make the parametric equation for the unit circle, my x function would be x of t equals cosine of t, correct? My y function would be y of t equals sine of t. Yep. But that's for the unit circle. Unit circle has a radius of 1. What if I want to expand that circle? What do I do? Excuse me, what do I do? So if I want to graph a circle with radius of r using parametrics, that's going to be x of t and y of t, right? What is my x function going to be? X of t is going to equal what? R times the cosine of t. What's y of t going to be? R times sine of t. Where are those circles all centered? At the origin. If I didn't want to center it at the origin, like let's say I wanted to shift my circle to the right 7 units. What tweak would I have to make?
Do t plus, or yeah, t minus 7.
No. That one? It's actually pretty simple. Well, if I wanted to shift it 7 units to the right, I'm just going to, right? Yeah, I said right. I'm just going to say add 7. Because the right is positive, right? Yeah, right's that way. Plus 7. And now my center is at 7, 0. Now, why is that confusing for you, thinking back to conic sections? Because in conic sections we thought about opposites. Because in math, if it's inside a set of parentheses, we think oppositely. Okay? Is this inside parentheses? No, so it's straight up. So if I wanted to shift that circle 7 units to the right and down 15 units, okay, so I'd have plus 7 there because that shifts it to the right, and I'd have minus 15 there because that would be then down 15 units. Okay. If I wanted to go up and left, okay, so if I wanted to go up 4 units, where would I put the plus 4? On the x or on the y? On the y if I want to go up 4 units. If I want to go left 17 units, on x or on y? On x, and it would be minus 17. Okay? Those are all straight ups in parametric, which is why parametrics are much easier to use. Okay? Because they're straight up. You don't have to worry about thinking oppositely on certain things and not on the other. Okay? So what is the parametric equation of a circle centered at the origin with radius of 30? Cosine of t and 30 sine of t for my y. That's centered at the origin. What if I tweak those centers and I say, what if the center, same circle, what if the center is now at negative 5, 18? 30 cosine of t minus 5. Okay. And What if my center is at 0, 25? So that one stays normal. And okay, with me? All right. Let's get into some circular motion type stuff. What is probably the funnest, and yes, I'm using the word funnest, okay? What is probably the funnest use of circular motion that we have in this world? Orbiting the sun is not circular motion. I hate to break it to you. That's elliptical motion.
That weird game that you put a ball on your leg and hop in a circle.
What do you got? Wolfie? A Ferris wheel is probably the funnest use of circular motion that we have. Okay? Okay? Alright? Because with a Ferris wheel, if you're riding the Ferris wheel, okay, so if you start over here, okay, and you go around the Ferris wheel, you have vertical motion and you have horizontal motion at the same time. Okay? So that's a great use of. Now, there's some cool Ferris wheels out there. We were talking in the last class about some of the cool Ferris wheels out there. Okay? There's, small ones that you see at like carnivals and, that kind of a thing. Or at Bay Beach, there's a smaller one over in Green Bay. There's a huge one over in England, yeah. There's a huge one in Vegas now, apparently, that like the gondolas, they're called gondolas. The gondola is like a room, so you get up and you walk around, and like you're not even seating. And, there was one, I've been on one in Cleveland where they had to cut a hole in the ceiling, and it was kind of cool because you were inside the building, and then, so you see everything inside the building, and then when you get up to the top, now you're outside and you see the skyline of Cleveland and the airport and Lake Erie and all that fun stuff, and then you go back down through it. Okay? My $1 billion idea is you got a Ferris wheel, right? So when you're up top, you're overlooking like an aquarium. And then as you come back around, then you go down, you go into the aquarium. So you see all the fish and stuff underneath the water, and then you come back up and you see it again from the top. That's my $1 billion idea, but we figured it's going to take like $1 billion for just to build it. So, okay? All right? So, let's come up with an answer to this problem. And the problem is a Ferris wheel with a radius of 30 feet rotates counterclockwise at a rate of 1 revolution every 20 seconds. The bottom of the Ferris wheel is 10 feet off the ground. The question is, what position are you 22 seconds into the ride? Okay? So that's the question that we have. We have to answer this question. Where are we 22 seconds into the ride? All right? So, let's come up with our first draft of our equations. And let's stay in parametric mode. Okay, let's make a parametric of this. So my x function is going to be what? And my y function is going to be what? Okay. I've got a Ferris wheel, 30-foot radius, rotating counterclockwise once every every 20 seconds. Bottom is 10 feet off the ground. Come up with my x function, come up with my y function. What do you got? 30 cosine of t. Just that. And 30 sine of t plus 10. Do we like those two functions for x and y? Wait, uh-oh. Go ahead, Will. The plus 10 is wrong. Why is the plus 10 wrong? Okay, so this distance right here is 10, right? But where's my center? $30 more up, right? Okay, because the radius here was 30. So I don't like the plus 10. What do I like instead? Plus 40. Now I like the plus 40. Okay? I like that a little bit more because my center is at 0, 40. Right? Okay? Like it so far. Now, let's do a little logic action going on here. Okay. At t equals 5 seconds into this rod. 1, where am I? 2, what's the coordinates of the point that I'm at? 5 seconds into the ride. That's where we start. Okay? So the smiley face is where we start. So where are we, Sam? We're at the top. Why are we at the top? Yep. So I'm a fourth of the way around the circle, right? And if I'm going counterclockwise, I'm at the top then, right? Okay? Agree? Does everybody agree that 5 seconds into the ride, we're at the top of the Ferris wheel? What are the coordinates of the top of the Ferris wheel? Counterclockwise. Okay? What do we say for the 0.70? Do we agree with 0.70? Yes. Love it. Love everything about that one. Okay? Using some more logic. At t equals 10, where are we? What position is that? Wolfe? Left side? Left side. Okay? And 30, 40. I've heard negative 30, 40. I've heard 30, 0. You said no on that? Okay. I like negative 30, 40. Love it. Go a little bit more. T equals 15. Where am I at? What's that position? I'm on the bottom. Yes. Position is 0, 10. T equals 20. Where am I? Back at the start. Position 30, 40. Okay? Love it. Love everything about it. Now, to check, to make sure, because we know we're at those points, at those t values, to check, what I'd like you to do is I'd like you to check t equals 10 here. Okay? I want you to plug t equals 10 back into our first draft of our function, or of our equation, and see if we get negative 30, 40. I get 30 cosine of 10 as negative 25.1721, and I get y of 10 as 23.6794. Yes? Well, did you get that or not? No, I want you to just test that one point. Yeah? Back me up on those? Okay. Something's not stirring the Kool-Aid.
Oh, that bottom. Oh, wait.
Neither one of them works because neither one of them are negative. The x isn't negative 30 and the y isn't 40. Ruh-roh. What? Are you in degrees or are you in radians? What? That's what? You need to be in radians when you're dealing with parametrics.
I just typed there. Right half of it.
Okay? So what needs to happen here is we need to adjust our two equations to fit the period. Okay? Now, back in first semester, we were dealing with graphing trigonometric functions. We graphed sines, cosines this way. We could have graphed tangents, cotangents, secants, and cosecants this way, but we limited it to sines and cosines. We said y equals a times the cosine of b times the quantity x minus c, then plus d. This ringing a bell a little bit? Okay. In that, if we remember correctly, in that, a was our amplitude. That was the height, right, of our wave. Correct? Okay. Well, in this case, a, that's going to be our radius. Okay? B was our period. C was our horizontal shift. And D was our vertical shift. said that the period, if we remember correctly, the period was equal to 2 pi divided by b. Which means then that b is equal to 2 pi divided by the period. If I do some maths there, if I multiply both sides by b, divide both sides by the period, I get b equals 2 pi divided by the period. Okay. In a Ferris wheel problem now, so if I want to make that adjustment, my b is going to equal 2 pi divided by my period. So that's going to be 2 pi divided by, how long does it take us to get all the way around the Ferris wheel? 20 seconds. So that's going to be 2 pi divided by 20, which gives me a b value of pi over 10. Okay. So my final equations, hopefully, we're going to test them out here. My final equations x of t is going to equal 30 cosine of pi over 10 times t Whoa, way too much. Forgot to change the size of said eraser. And y of t is going to equal 30 times the sine of pi over 10t plus 40. Okay? Now, what I want us to do is I want us to graph that function. So I want us to graph our final equation function. You get it up on the top there, and then I can pull this down to there. Now we can see it. So then we need to make a new, I like to be on a fresh new page here. Graphs, I want to be in parametrics. Whoa, hey now. I want to be in parametrics. And what color? Let's go 3, we got 4, we got 5. Let's see what color 6 is. Okay. So my first one is 30 cosine of, now I got a fraction, pi over 10 times t. And then I've got 30 times the sine of, again I have a fraction, pi over 10 times t, then plus 40. There we go. Okay. Yes? So when I hit enter, I should see my Ferris wheel, correct? What? Why do I have to adjust the window? Because, what do you mean it's big? It's got to raise 30, so I for sure got to go 30 in each direction, left and right, correct? And I'm only going 6 2/3 feet off the ground, so I for sure got to adjust my window. Okay, so let's go in and adjust our windows. Now, let's pick an appropriate window setting. So we've got to go 30 feet in either direction, to the left and to the right, correct? So let's go 40 then. Just because then we can see out there. Do I need to go negative? I hope your Ferris wheel doesn't go underneath the ground. Better not be stealing my idea. I do like to see my horizontal axis, so I'm going to leave it as -5 down there. Maximum 80, okay, because we need to get up to 70, right? So let's go up to 80, and I'm going to go by 5s again. So now I should see. That's. Uh-oh. Why don't I see a full circle? No, I don't know.
That was, yeah.
What do I got to adjust? But with my T's, right? Not my T step, but what my T's are. This is only going 6.28 seconds. How long does it take me to get all the way around? 20. So that 6.28 has got to be a 20 in there. Whoa, too far. So this right here has to be 20. And now I get this. Now, you may be saying to yourself, Linz, I don't trust this Ferris wheel. Okay? It's not the Ferris wheel. It's more along the lines of, we just got to, whoops, tap the brakes, this one. I just have to square up. If I square up my window, then it brings it into proportion. Okay? So then it becomes a complete circle again. Okay? Alright? So that's my Ferris wheel now, which, if I were to trace around it, so let's go menu, tap the brakes, I gotta go here. This has got to be trend. Then I want to go menu. I want to trace step of 1, because I'm going to go every second. Makes it easier. And then I go menu, and then I go trace. And now I trace around this at 15 seconds, which is where I'm at. I'm at the bottom. Logically, that's what we set. At 15 seconds, we should be at the bottom of the Ferris wheel, which is at the point 0, 10. Yes? Love it so far. If I scroll, if I key to the right at 0, this is where I load. I'm loading on the right side. This was our smiley face before, okay, which we said was at the point 0, 40. At 5 seconds, we were at the top. We said that was 0, 70. Just been confirmed. At 10 seconds, we said we were on the left side. -30, 40. Confirmed. We already confirmed the bottom. We got our Ferris wheel. Okay? Now, I'm going to go back to 0. So here I am at 0. Okay? All right? Let's ride the Ferris wheel. 20 seconds, I'm back at the start, right? So to get to 22 seconds, because that's what we wanted to find, is our position 22 seconds into the ride, where do I have to go? What? 2 more seconds. So there's 1 and there's 2. Okay? Or what I could have done is I could have gone into my t values and I could have made that, instead of being 20 seconds, I could have made that be something bigger than 20 seconds. like 22 seconds and then gone right to 22. Okay? So that's my position 22 seconds into the ride. So I'm 24.3 feet right of center, and I am 57.6 feet above ground. As my position. Okay? Now, let's talk some tweaks that we can make on that very same problem. Okay? So my functions were, or my function was, x of t equals 30 cosine of pi over 10 times t, and y of t equals 30 sine of pi over 10 times t plus 40. Okay? We were going around in a counterclockwise unit circle direction, correct? Okay? What if I wanted to spin that? What if the carny decides he kicks it in reverse, and now we want to go in a clockwise direction? What tweak needs to be made? If I want to go in the opposite direction, or if I'm standing on the other side of the Ferris wheel that you are. So like if we're looking at the Ferris wheel here on the table, if I'm standing on this side, it's going around in a counterclockwise direction. But if I'm you, it's going around in a clockwise direction. Okay? What tweak needs to be made? Do you understand that one?
I don't believe that's true.
Okay. For me, it's going around in a counterclockwise direction.
Yeah, well, I'll take your word for it.
What tweak? Anybody know?
Negative t.
Not negative t.
Oh, negative coefficient of t.
So a negative b value, right? So if your direction states that you're going in a clockwise direction, your b value has to be negative. If your direction states you're going in a counterclockwise direction, your b value has to be positive. Because that's the unit circle. That's where that comes from. That comes from the unit circle. Okay? Now, when you've ever gotten on a Ferris wheel, have you ever gotten on the right side? I don't know if I've ever gotten on the right side. So what happens if I said we want to get on at the top? Which means we start at the top.
Which means your dream is real.
Exactly. Or, let's say, what if we wanted to start at the bottom? Normally you start at somewhere close to the bottom. What tweak needs to be made? Nope. 40 is my vertical. That changes my vertical part. The what? That's my period. So inside the set of parentheses, so in here, in that part, it would be b times t plus pi over 2. If I'm starting at the top. If I start at the bottom, okay, what if I don't like that big of a fraction? I could subtract pi over 2. What if I want to start not on the right side, but on the left side? Plus pi or minus pi. Yep, either one would get me to the other side. Okay. Those are the major tweaks. So the major tweaks are where you start and which direction you go in. Okay. For a Ferris wheel type of problem. Okay. That concludes today's Ferris wheel carnival fun. Okay. Now we still have about 20 minutes, which is 20 minutes that you could start working on your purple packets so that you didn't have to do your purple